Okay, we have a series here. Is this series convergent or divergent? So with this one, we could do the integral test. We could do the integral test for two reasons. The first one is that this is monotonic decreasing. What that means is that no matter what you plug in to the sequence, each term of that sequence is going to be decreasing. So the series itself, if you have positive, you're always adding, right? So it's always going to be increasing. The series itself, the sum, is increasing if you're summing positive numbers, even if those positive numbers are decreasing. So the series is increasing. But let's remember the difference between a series and a sequence. The sequence is just the terms themselves. So the terms themselves are decreasing in this case because we plug in 1, then we plug in 2, then 3, then 4, and your denominator is getting larger and larger and larger. That means the fraction as a whole would be getting smaller and smaller and smaller. So that's the first thing we want to make sure. The second thing that we want to make sure, besides that this is monotonically decreasing, so always decreasing, the other thing is that it's always positive. We can't have negatives from 1 to infinity. So is this always positive? Yeah, because we're multiplying by 2, and here we're plugging in the denominator positive numbers from 1 to infinity. So it passes our two checks, which means we can apply the integral test. So with the integral test, we just take the integral of what's inside. And the integral would give us wow, this is really bad. This is really bad. Is that visible? I don't think that's visible. Technical problems. Okay. So we take the integral test here by just taking the integral. That's better, okay. And this would be how we would do it. We get from 1 to infinity. From 1 to infinity, but let's remember we can't directly work with infinity when we're doing integrals. So this right here would become a t. This is a t, and we take the limit as t approaches infinity. Now we can actually solve our integral. So if you remember with this, we have something which is a fraction of this form. So when we take the integral of that, we get the natural log of what's in the denominator, absolute valued, 5n minus 1. Then we're multiplying this by 2, and then we take 5 from here. It's kind of like the chain rule, like we have 5n minus 1. You ignore the constant and you divide by this. So it's just a quick way of evaluating the integral. So that would be bringing out 1/5. Multiply 1/5 by this, you get 2 over 5. That's natural log, and these are absolute values. So now we take this we evaluate that from t, from 1 from here to t, and we take the limit as t approaches infinity. So remember, we take the upper bound and subtract the lower bound, which is this. So we have 2/5 natural log of the absolute value of 5t minus 1 minus plugging in 1, and that's going to give us 2/5 natural log absolute value of 5 minus 1, because 5 times n being 1 would give us 5. So that's what we have. We take the limit as t approaches infinity. So that would be plugging in infinity into this t here. That's the natural log of infinity because you multiply infinity by 5, you subtract 1, doesn't matter, still infinity. Natural log of infinity goes to infinity. Remember, it has no horizontal asymptote. It just keeps going, increasing and increasing. So this is a constant. It doesn't even matter what that evaluates to, really, because you're subtracting some constant from infinity. Infinity will take it. So this is infinity, which means that our series diverges.